Flying today feels almost aggressively mundane. You board a metal tube, find your seat, complain about the legroom, and settle in for a bus ride in the sky. But look at this graph plotting altitude against atmospheric pressure. At sea level, we breathe air at 14 pounds per square inch. But at a cruising altitude of 35,000 feet, pressure drops to a lethal 4 psi. At that height, the oxygen is too thin to sustain consciousness, the temperature is consistently sub-zero, and the friction from pushing through the air at 500 miles per hour builds up massive amounts of static electricity on the metal exterior. So how does a relatively thin shell of carbon fiber and aluminum keep you perfectly comfortable while hurtling through an environment that would otherwise kill you in minutes? A commercial jet is a lot more complex than a passive transport vehicle. It is a sealed survival capsule that actively manufactures a habitable microclimate to keep those extreme elements out. The first line of defense is the airframe itself. Thousands of individual carbon fiber and aluminum panels are riveted onto an underlying skeleton of vertical frames and longerons. This creates a strong, lightweight shell, but not the whole plane holds breathable air. Only specific areas, the flight deck, the passenger cabin, and the cargo base below, need to maintain that Earth-like atmosphere. This diagram shows a cross-section of the fuselage. The colored sections represent the life-supporting areas, which are physically sealed off from the unpressurized tail cone and landing gear bays by reinforced metal barriers known as pressure bulkheads. Trapping 14 psi of air inside a sealed tube before takeoff only solves half the problem. If you pack hundreds of people inside a closed container, the breathable oxygen naturally depletes. The physical structure simply holds the environment in place. The aircraft has to continuously manufacture and circulate fresh, breathable air while flying. To accomplish this, the aircraft relies on the exact same things propelling it forward. The jet engines double as the plane's primary life support system. Before combustion, hot compressed air, bleed air, is siphoned out. It passes through ram air ducts, cooling by mixing with outside air, then pumps into the cabin for fresh oxygen. A secondary stream travels through perforated tubes along the wing's leading edges, melting accumulated ice. Every breath a passenger takes, and every patch of clear wing surface, relies entirely on the continuous mechanical rotation of the engine core. Pushing a massive metal object through the atmosphere at high speed creates immense friction. That friction forces the airframe to constantly build up dangerous levels of static electricity. To prevent static from interfering with electronics or causing a spark, flexible metal rods on the wingtips safely bleed this electrical charge off the airframe and back into the atmosphere. Managing stray sparks is especially critical because the hollow internal structure of those wings holds thousands of gallons of highly flammable jet fuel. Here inside the fuel tank, standard air poses a massive fire risk. To neutralize this, bleed air from the engines is processed through a separator to remove the oxygen. The resulting inert, nitrogen-rich air is pumped back into the tanks to fill the empty space, making accidental combustion nearly impossible. Heat buildup is also a major hazard on the ground. During heavy braking after touchdown, the wheel assemblies easily exceed 200 degrees Celsius. To stop the massive tires from swelling and blowing out, thermal fuse plugs built into the wheels melt at that exact temperature, safely releasing the internal air pressure and cooling the brakes. The aircraft is engaged in a continuous battle, bleeding off electricity, suffocating potential fires, and venting extreme heat to neutralize the forces generated by its own movement. But operating in such a hostile environment means that eventually a mechanical component will fail mid-flight. Look at this wireframe map of the plane's hydraulics. Aviation engineering relies heavily on redundancy. Rather than trusting a single point of failure, there are 3 entirely separate and overlapping hydraulic circuits connected to the vital flight control surfaces on the wings and tail. If one springs a leak, the others immediately take the load. If the main engines lose power, an auxiliary power unit, or APU, sits in the tail cone. This independent gas-powered backup generator spins up to supply the electrical power and pressurized air needed to restart the primary engines. And if all conventional power fails, the ram air turbine deploys. This small propeller-like device drops automatically from the bottom of the plane, using the rushing wind of the aircraft's forward momentum to generate enough emergency electricity and hydraulic pressure to safely steer and land the plane. Commercial airliners boast an incredible safety record because the entire machine is systematically designed with overlapping fail-safes built specifically to survive its own mechanical breakdowns. The low hum of the cabin, the steady stream of air, the slight bumps during descent, these mundane details mask a highly active network of bleed valves, nitrogen pumps, and thermal fuses working in unison. The human body is entirely unequipped to survive freezing temperatures, a near-vacuum atmosphere, and the sheer friction of high-speed flight. The commercial airliner is an actively functioning fortress. It is mathematically layered with mechanical defenses to carry fragile human cargo safely through the deadliest environment on Earth.